Hi everyone, this is Yongshu from Microsoft Research Asia. Here I'm going to introduce our work, CARE, which is a causal aware engine for root cause discovery, on behalf of our team. Actually, more important purpose of this talk, I think, is to raise your attention on causal aware thinking when conducting root cause analysis in cloud systems. Nowadays, with millions of customers accessing online service all over the world, cloud service reliability is very critical. To ensure high service reliability, monitors are widely spread on various system components to track their behavior over time. Some automatic anomaly detection pipeline was set up, and once an anomaly detected, alert will be fired and calls for operators and engineers to investigate. Previously, a typical diagnostic process involves much human effort. When some complex problem occurs, on-call engineers may even need to gather related teams to investigate together, which makes the troubleshooting process slow and thus postpone the recovery action and affect service reliability. In recent years, a trend of data-driven anomaly detection and root cause analysis is emerging. The abundant system-generated data, like logs, telemetry signals, and KPIs, provide a big opportunity to unveil the system pitfalls. For example, the IDAS and FDA is able to automatically locate the anomalous dimension combinations, and the machine learning-based method like the CAF learns the suspicious features from data. The mining and learned result provide hints for developer to take recovery actions. The advanced data mining, machine learning, and even deep learning technology has been regarded as a core engine to improve the time-consuming and arduous diagnosis experience. Although the existing solutions could be enabled to provide useful hints, they are by naturally insufficient for concluding the root cause. The reason is because technologies based on observed data can only give statistical correlation rather than the root cause, and they may meet trouble when there are confounding factors and database issues. The table shows an example in service deployment scenario. The high correlation between the version 1.1 and the failure signal will conclude that the deployment should be blamed for this fault. However, the machine type is actually the root cause for these burst failures. But since most version 1.1 was deployed on Gen 6 machines, the correlation shows high score and make a wrong decision to roll back the version. And this box plots show the time of VM creation on 88 different devices. As we can see, the signal distribution of them differs from one another. And these are not uncommon in the heterogeneous cloud system, where the machines are with different properties like hardware types and different workloads. We may also meet data bias in temporal dimension. With the time goes by, the data distribution may be drifting. Even you can specifically design the technologies to conquer these issues, there are unobserved factors like runtime change or other unexpected interruptions, which cannot be tracked in the data. So, how can we trust the collected data in delivering the true root cause remains a question. In this work, we propose to infuse causal aware thinking to step further towards root cause discovery. Instead of passively collect system-generated data, we aim to proactively intervene in the system so that the analysis based on the collected data could rule out the impact of data ambiguity issues. As we know that cloud reliability is mainly threatened by all kinds of changes, like service update, configuration change, etc. Let's call these actions. So instead of passively collect the data after the action, CARE leverages the idea of random control trial designed to set up a testing environment. The action will be taken in the treatment group, and then we collect the signals of both the treatment and control group to assess whether the action is good to go or risky to stop. The RCT design is widely applied in medical care, which offers causal inference through random assignment so that the influence of other known and unknown factors could be eliminated. When conducting RCT, an important thing is to properly choose a set of samples on which the response could generalize on the whole population. The simple random sampling is the best, but usually not practical and pretty expensive. In cloud system, the computing resource is very precious, so we adopt stratified sampling, where the whole population is divided into subgroups and the samples are randomly taken from each group. Here, to identify the subgroups, we use a decision tree to categorize the target scope of machine. For example, we can use the historical signal value on each machine as a metric to construct a tree, and then randomly sampling within the lymph nodes to compose the treatment and control group. In this way, we can make the treatment group as diverse as possible and also make the control group similar to the treatment group so that the machine-related factors could be ruled out. And when doing the assessment, we adopt a DID method, which is widely applied in economic and healthcare areas. As we can see from the illustration, this method could eliminate the temporal bias by deducting the value of y before the action time on both treatment and control group. The framework of care has been applied in service deployment scenario in Microsoft for both Azure and Office 365. Here is an example case of change deployment. Before applying care, there is an alert on configuration change. And during the investigation, we find that the change is only deployed on machines with a certain app version. And unfortunately, the app version is exactly the root cause rather than the configuration. So actually, on the moment of the configuration change, there are various app versions in the environment. When applying care, a treatment group with diverse versions will be selected, and the signals treatment group and control group has nearly no difference. So we would successfully prevent the false alarm. Here, the version 3349 is not included the chance, but even the version is included, we will not blame the configuration change because it performs normal on other versions. So in summary, in this work, we propose the idea of infusing causal overthinking for root cause analysis in cloud system and demonstrate a system design care based on the idea and show its application in deployment scenario. And as mentioned in the beginning, we suggest to implement the idea in decision-making process in your scenarios. And we think how to economically design the RCT experiment in complex cloud would be worthy for the future study. Thank you for listening. Any questions?